Hi everyone. In this last example from the previous video, we got told that a vector of the form negative t, 2t, t is a solution to this system of equations. We have a particular vocabulary for this. We say that this particular system of linear equations has a family of solutions. We call it a family because the solutions are related to each other through a variable t. Some families of solutions have more than one parameter in them. I said variable, I meant parameter. So you might have a family of solutions with a t parameter and an s variable, and maybe with an r parameter. So an r parameter family of solutions just indicates how many parameters there are in there, whether you have freedom to choose anything you want for t, or freedom you have to choose anything you want for t and for s. And you'll see what I mean when we get to these examples. Because the previous example had only one parameter in it that linked the different members of that solution family together, we would say that that system has a one parameter family of solutions, just t. Solving a system of linear equations means either showing that there's one or more solutions, or showing that the system is inconsistent, showing that there is no answer. So as you're going through a process of substitutions and eliminations, this would be indicated by ever coming across a statement that looks like 5 is equal to 0 or 2 is equal to 1. Anything that's nonsense. If that happens in the process of solving a system of linear equations, and you didn't make any mistakes, then it means that the system doesn't have a solution. So we have to do one of these two things to find an answer, or to cap off a question. Sometimes it's really easy, like this one. We have a system of linear equations, x plus y is equal to 1, and the other equation is y is equal to 0. What makes it simple is that the second equation directly tells us what one of the variables is. It tells us that y is 0. We can do back substitution. We can replace the y in the first equation with 0, knowing what it is, and then solve for x. So it says that x plus 0 is equal to 1, which means x is 1. Immediately, we can thus state that the solution to the system of linear equations is 1, 0. X is 1, y is 0. We can be confident that there's no other key that will open this door, that there's no other solution to the system of linear equations, because there's no other interpretation for the second equation. Y is equal to 0 unambiguously. There's nothing else that can be true. Likewise, when we plug that into the first equation inside the system, it unambiguously states that x is equal to 1. There is no alternative. There's no parameter lurking. There's no infinite set of solutions. But sometimes it's not straightforward. Sometimes we look at the system and we know that we have work to do. The work that you would have done in a previous course, grade 9, grade 10, would have been to use a sequence of operations called substitution and elimination. We'll do that a little bit more. Then what we'll do is we'll kind of become more advanced. We'll learn a better method, a better strategy. By the way, that strategy is still related to substitution and elimination, but it's more systematic, it's more reliable, and it involves a lot less writing. This approach will involve defining and using only 3 operations. So some students often will say that math1229 is a course where you do adding, subtracting, multiplication, and division. You just have to keep track of the order in which you do those things. I would say that accurately describes this part of the course, because what we will be doing is just adding, subtracting, multiplying, and dividing. It's the order in which we do those operations and the sheer number of those operations that makes it sometimes unpleasant. So even though each step is really simple, it's the collection of steps that can make things complicated. You're going to make mistakes when you're doing this, and I'm going to make mistakes when I'm doing this. And there's going to be a lot of corrections inside these videos. So, to solve a system of linear equations or determine that there is no solution, we will follow this particular set of operations. We'll have different notations for these operations as we move along inside this section, but to start things off, the first operation is that we can add equations and we can multiply equations by a constant. So for example, we can add these two equations together. The x plus y is equal to 1. We can add that to the x plus 2y is equal to -2. I would not recommend doing this if you had these two equations inside a system. It doesn't get you any further, but this is what it would look like if you were to do that operation. You have the x plus the x, you have the y plus the 2y, and you have the 1 plus the -2. You'd group the terms together. So the x and the red x and the blue x gives you a 2 times x, and the red y and the blue 2y, when you add those together, that gives you a 3y. And then the 1 plus the -2 gives you a -1. You can drop all the colors once we add them together, or just not have colors at all if you don't want. Now this did not help us. This got us no closer to having an answer. We could have also multiplied by a scalar. So let's say I multiplied a third equation, 2x plus 3y minus z is equal to 5. I want to multiply that by 2 for some reason. So then I would get 4x plus 6y minus 2z is equal to 10. I have to make sure that each component, each piece of the expression gets multiplied by that scalar. Otherwise, I no longer have that equal sign being true. To maintain the equal sign, I have to do the same thing to both sides of the expression. So our elementary operations, just to state them, we can multiply any equation we want by a constant. That's the first one. The third one, we can replace one equation by itself plus a multiple of another equation. So we can add two equations together. We can also subtract one equation from another one. Or, I didn't do this, but we could take one equation and add twice that equation to another equation. Just do it twice. So I'm going to add equation 1 to equation 2, and then I'm going to do it again, which is equivalent to saying equation 2 plus 2 times equation 1. And then the middle operation there, operation 2, is kind of a do-nothing operation. Like, it doesn't change anything. It's to interchange the position of two equations inside the system. So let's say you have a stack of 3. I'm just going to switch the order in which the first 2 are written. So what was now the top of the stack is now in the middle, and what was previously the middle of the stack is now at the top. It doesn't change the data. It doesn't truly get us closer to a solution, but we will have that as a permitted operation anyway, and you'll see why later. It's important to note that this is all that you can do. You cannot do anything else. You cannot square both sides. You cannot do substitution. You have to abandon substitution. You also have to resist the temptation to do what I did when I was learning this, which was try to solve everything with substitution and elimination. Go back to my grade 9, grade 10 math and solve things that way. So I fought hard against doing what we're about to learn how to do. And as a result, I could not finish my test. I could not finish, like I took this course, I couldn't finish the first test. Or rather, it was the second test. I couldn't finish it. Because that old way is way too slow. So you're gonna have to abandon it even though you don't want to. When you see what we're about to do, you're gonna say, no, I'm just gonna keep doing it the old way, thanks. You won't finish. You'll run out of time. It's not efficient. All right, so let's solve this particular system of linear equations using only those 3 operations and resisting the urge to say, the second equation says that x is equal to 1 plus y. I'm just going to sub that in for x in the first equation and solve for y and then find what x is. We're not going to do that. So what I'm going to do first is I'm going to call this equation 1 and call this equation 2. And I'm going to take equation 1 minus equation 2. So I'm going to subtract one from the other one. Or you can think of this as equation 1 plus -1 times equation 2. So the first equation is going to be x minus x, which is 0. 2y minus -y, which is 3y. I'm subtracting a negative. And then 4 minus 1, which is 3. And my second equation, I'm not going to change, I'm going to leave it alone, is x minus y is equal to 1. So again, 0 came from x minus x. The 3y came from 2y subtract negative y. So subtracting a negative is the same as adding a positive. And then the 3 came from 4 minus 1. So that was the first move. Now we're going to do the second move. Now, I know what they are. I know it all. I memorized them all, but I'm going to go back to those operations and look at what we're allowed to do. We can multiply an equation by a scalar, interchange positions, replace one equation by the sum of that equation and a scalar multiple of another. So that's the one we just did. We did the third one. Now I'm going to do the first one. I'm going to multiply by a scalar. I'm going to say equation 1 multiply by 1/3. I'm not going to change equation 2. So I'm going to get 0 times 1/3, which is 0. 3y times 1/3, which is just y. And then 3 times 1/3, which is 1. And then the second equation, I'm not going to change. X minus y is equal to 1. All right, next step. We know what y is. And you're thinking, okay, so y is 1, x minus y is equal to 1, so I know what x is. Like I just substituted it in, but I'm not going to do that. I'm only going to use the operations that we're allowed to use. So that's going to be replacing one equation with the sum of that equation and a scalar multiple of another one. You can do subtraction if you want. It won't get you any closer to the answer. It's better now to use addition. I'm going to add. I'm going to take equation 2. I gotta be careful. I'm going to replace equation 1 with, here I'm going to replace equation 2 with equation 2 plus equation 1. So this is move 3. So equation 1, we're not changing inside this move. We have 0 plus y is equal to 1. And now we're going to have x plus 0, which is x, y plus minus y, which is 0, and 1 plus 1, which is 2. Now I'm going to do a really strange thing. Who is this guy? Why is he doing this to us? I'm going to swap order of E1 and E2. I'm just going to write them in the other order. So now it says that x plus 0 is equal to 2. When I do this swap, I have to make sure I swap the left-hand side and the right-hand side. And 0 plus y is equal to 1. Now we can make a conclusion. Conclude x is 2, y is 1. And you could have done that much faster using substitution and elimination together. Like you could have done that in 1/10 the time. So you are rightfully now asking yourself, why did I just show you this if it's so inefficient? And I'm going to tell you that there's a crossover point based on how complicated your system of linear equations is, how many equations and how many unknowns, where a process like this becomes much faster than the substitution and elimination method. So for small systems like this, yes, substitution and elimination is quicker, but for large systems, this approach is way faster and more reliable. And it also tells you, with less ambiguity, when there's no solution to the system of equations, which is very hard to do when you're using substitution and elimination. All right, next example. Find all solutions to this system of linear equations. So I'm going to write this down in a slightly different way so it's easier to keep track of. My thinking process is I want to get rid of pieces of the expression. I want to make pieces of the variables disappear. So for example, if I replace equation 2 with equation 2 minus equation 1, that will make the y part completely disappear. So equation 2 replaced by equation 2 minus equation 1. What you'll notice I'm always doing is I'm always replacing an equation by itself plus or minus something. That's important. You always want to involve the original equation with what it's being replaced by. So it's always replaced by itself plus or minus something if you're using this move. The first equation did not change inside this move. The second equation is the one that changes. So I have 2x minus x, which is x. I have y minus y, which is 0. And then I have 0 minus z, so negative z. And then 10 minus 5, which is 5. Third equation did not change, just y plus 2z is equal to 0. Okay, next, what else can we do? Maybe I should have subtracted twice that. Maybe that would have been smarter. It's hard to know. But let's keep going. What else can we do? Maybe we can get rid of the y in the first equation now. So notice that equation 3 has a y and a z and no x. Equation 1 has an x and a y and a z in it. It's going to be possible for us to get rid of the y in equation 1 if we replace equation 1 with equation 1 minus equation 3. So that's the next move. So E1 replaced by E1 minus E3. So we have x minus 0, which is x, y minus y, which is 0, and z minus 2z, which is minus z, and 5 minus 0, which is 5. So that's all the change we're doing there. Second equation, we have x plus 0 minus z is equal to 5. And the third equation is y plus 2z is equal to 0. Now look what we have. The first equation and the second equation are identical. So what I'm going to do next is I'm going to replace equation 2 by equation 2 minus equation 1. So E2 replaced by E2 minus E1. So E1 is the same. We're not going to change that inside this move. X plus 0 minus z is equal to 5. And we have x minus x. 0 minus 0. Negative z subtract negative z. So it's negative z plus z, 0. And 5 minus 5 is 0. Okay, and then I'm going to do another move. I'm going to swap order of equation 2 and equation 3. So if I do that, I'll have x plus 0 minus z is equal to 5, y plus 2z is equal to 0, and 0 plus 0 plus 0 equals 0. And believe it or not, that's as far as we can go. We can't say anything else about the x, the y, and the z, other than letting z equal a parameter. If I mess with this further, if I replace equation 1 with equation 1, let's say plus 1/2 of equation 2, that'll get rid of the z, but it'll now introduce a y. I can get rid of the z in equation 2, but it'll introduce an x. I can't make it any better than what is already there. So what we would do is we would say, I'm going to let z equal t. Let z equal a parameter. Then I'm going to write my x and my y in terms of this parameter. So x is equal to 5 plus z becomes 5 plus t. Y is equal to negative 2z becomes negative 2t. And my solution is that x comma y comma z is equal to 5 plus t comma 2t, or negative 2t rather, forgot the minus sign, minus 2t comma t. This is a family of solutions. There's an infinite number of solutions. Pick anything you want for t, plug it in, and that will be a key that opens all these doors at the same time. This is confusing. I'll continue with more examples in the next video.